Hello students, welcome to Vista's Learning. I'm Harshitha, your chemistry tutor at Vista's Learning. Vista's Learning is an online education platform where we strive to provide quality education for all. So today's topic is going to be what exactly is activation energy and how do we know how the temperature is being dependent on the rate of the reaction, right? So we'll just see why exactly is this topic important, and we'll even have a recap of what we studied in the previous session. So what exactly was the topic that we studied in the previous session? Exemplar problems on half-life of a reaction. So half-life of a reaction, we understood what is the half-life of a reaction, and we saw a few problems as well. The next is pseudo first order reaction. So there was a first order reaction, second order reaction, then we had zero order reaction. All that we studied in the previous sessions, and then particularly in the last session we studied about pseudo first order reaction, right? So pseudo first order reaction is a reaction which is the second order reaction, but it determines and it has been found out which acts like a first order reaction. So that is the reason we call it pseudo first order reaction. Numerical on rate constant and order of the reaction. So we knew what exactly is the rate constant of the reaction as well as order of the reaction. So we solved a few problems which is important with respect to your exam point of view in the previous classes. As in, we solved a few exercise problems, few exemplar problems, as well as a few problems which is coming different varieties of problems that can actually appear in your exams. These are the things we covered in the previous session. So as I told, in today's session, we will be dealing with temperature dependence of the rate of the reaction. So how exactly the temperature is being dependent on the rate of the reaction? We must have actually seen, so if you're keeping any food, okay, any food, or imagine I'm just taking a fruit and I'm keeping it outside in a room temperature during summer season. Okay. So how many days do you think the fruit is going to remain fresh if it is kept outside in the same environment? So hardly 1, 2 or 3 days, right? During the summer seasons, when the temperature is quite high, the fruit gets spoiled earlier. The same case, if I'm taking the fruit and I'm keeping it in a refrigerator where the temperature is quite low. So when the temperature is very low and when the fruit is kept in the refrigerator, how many days do you all think the fruit is going to be fresh enough? It's going to be at least for like 5, 6 days, maximum 10 days if we are just taking for instance. So the time what we saw, time span for the fruit to remain fresh during summer as well as when it is kept in refrigerator when the temperature is low, it varies a lot, right? So this is how we can say the temperature is being dependent on any kind of reaction. Temperature plays a major role in the determination of rate of the reaction. This is just an example like how exactly we can see the temperature around us plays a crucial role to determine the rate of the reaction. Okay, so we'll study it in a detailed manner with respect to different types of reactions in the in this session. Okay, so for this temperature dependence, there's one important concept that we have to learn, that is our activation energy. Activation energy is one such concept which is very important from your chemical kinetics point of view, right? So your physical chemistry, chemical kinetics as such, any of the higher studies if you are doing with respect to chemical kinetics basically, or with respect to physical chemistry basically, this activation energy is a basic concept that should be known to you all. Okay, so we'll be understanding what exactly is activation energy as well in today's class. Clear? So without any further delay, we'll start off with the first topic, which is temperature dependence of the rate of the reaction. So this concept, how exactly the temperature is being dependent on the rate of the reaction, was given by J.H. Van 't Hoff. Okay, so Van 't Hoff was a Dutch scientist who actually proposed this entire thing. He described this entire process, but Arrhenius was one such scientist who came up with the interpretation. So he told the entire mathematical formula, he came up with the mathematical formula based on which we are going to be studying this entire process. That is the reason we call the Arrhenius equation, because we call the equation for temperature dependence of the rate of the reaction. There's a one particular equation. We call it as Arrhenius equation because Arrhenius was the person who came up with the interpretation. Though all the work and proposal and everything was done by band off. Clear? So what exactly is Arrhenius equation? Arrhenius equation is K is equal to AE to the power E to the power of minus EA by RT. So what is K? K is our rate constant, right? So with our rate constant, we can know the rate of the reaction, correct? A is our Arrhenius factor. And what exactly is E to the power EA by RT? EA is going to be our activation energy. So that is what we are going to be studying right now. Activation energy. And R and T. R is our rate constant, T is the temperature, right? That is already known. So now we are going to see how exactly from the equation the rate constant is being dependent on all of these factors. So first A, Arrhenius factor is constant, okay? It's determined for different reactions, it's different numericals will be there. So it is a predetermined value, as well as EA is the activation energy. So activation energy will be studying further. R and T. So we know the gas constant as well as T is the temperature. So at what particular temperature, how exactly the rate is going to be changing. That is what we are going to be studying. So now, what exactly is activation energy? So I told you the rate is going to be dependent on the temperature, right? So temperature and rate are interrelated to each other. So where exactly this activation energy comes up or comes into play is, so we'll learn it with an example. Basically, activation energy basically is the energy that is required, minimum energy that is required for the reaction to take place. That is what is activation energy. Any reaction to take place, we need to provide a minimum amount of energy to the reactants in order to form the products. Okay. So we know when the reaction is taking place, the reactants will be having certain bonds, right? So the bond breaking of the reactant as well as the bond formation of the product, this entire process will require a little bit of minimum energy than the energy what already the reactant is having. This is called as activation energy. So that's what is the definition for activation energy. In any reaction, the minimum energy required to break bonds and form new bonds, this minimum energy is known as activation energy, as I told you. So how will we understand this clearly? Now, uh, I'll take a, I'll plot a graph and I'll make you all understand in a simpler way. Okay. So there's a hill. Fine. So here there is a boy. Okay. And here there is a sphere. There's a ball. Fine. But there is a hill here on top and the boy wants this ball to be reached here. Okay. This is where the boy wants the ball to be reached. This entire thing is the reaction. Imagine this is the reaction coordinate. This is what we want to, this is what we want to be taken place. So this will be reaction coordinate. And what exactly will be this? This will be our potential energy. As in, there'll be certain amount of energy already there with the ball. The ball also will be having certain amount of energy. Now, is it, will the ball move on its own because it has its own energy, as I told you right now? Will the ball move on its own and pass this entire barrier and then reach here? Is it possible that way? No, right? It requires a little bit push. So it requires a push from the boy. That is the minimum energy that is required in order to, sorry, yeah. So in order to cross this barrier, this energy, what is required? Okay, this is what will be the energy basically of the entire barrier. Okay, this will be the entire energy of the barrier. And this entire energy of the barrier is known as threshold energy. So what is this called? This is called as threshold energy. Okay, so this is a certain energy, amount of energy which is required in order to make sure the ball is being passed. Okay, total energy of the barrier, threshold energy barrier is what we call this. but the person is already having certain amount of energy. So imagine from here to here, okay, there is 30 kilojoules, okay, 30 kilojoules energy which is already there with the boy. Okay, but it requires so much more amount of energy in order to cross the barrier. So this amount of energy, what is required? Let me use another color. Okay, this amount of energy, what is required? This is called as activation energy. So certain amount of energy is what they already have. So this is total, imagine this is going to be a total of 100 kilojoules that is required. So 30 minus 100 minus 30 is 70. So 70 kilojoules is the minimum energy that is required for the ball, that is we need to provide in order to pass the threshold energy barrier. After that, it is reached the top of the hill. Okay, so after that, it's easier for it to go down, right? Because we know the hill is being steep, right? From here, the ball can move very fast. So we can see from the threshold energy, the ball can move really fast and it will reach the place where it has to reach. This threshold energy barrier, what is there, and this activation energy, what we tell the minimum amount of energy is what we provide. If this is being passed and if this is being provided a little push from the ball, then it is going to reach the product. This way the ball moves and here it reaches the product. So this will be the energy of the product as well. So imagine this is going to be 10 kilojoules. Okay, so here from this part, okay, this is known as delta H. Okay, this is our delta H. Fine. Now you all understood. I hope you all understood what exactly is a threshold energy and what is activation energy. Why exactly activation energy is required. I hope you have understood all of these. Okay. Activation energy is the extra energy that we provide for any of the forward reaction. This same thing we will see with respect to reaction, a reactant giving product. Okay. Now, plot of potential energy versus reaction coordinate. As I told you, right now I'm going to explain with respect to chemistry. Okay. Before that, I just told you with a random example. Now we'll see in terms of chemistry. Now, a reactant is going to give a product. That's what is basically a reaction, right? Reactant is giving the product. In this, we are going to be plotting a graph, which is going to be the reaction coordinate on the x-axis. And we have potential energy. That is the energy which already the reactants will be having. So this particular point will be where the reactants are there. Okay. Imagine ER is going to be the energy of the reactant. Okay, the potential energy of the reactant. Now, we want the reactant to form the product, but we know there is a barrier that it needs to cross. So once it crosses the barrier, it reaches the complex. Okay, it forms an intermediate stage in between and then it forms a product. Where is this intermediate forming? It is forming where we reach the barrier. Okay, when it crosses the barrier, that's when the intermediate forms, and then once it's crossed the barrier, we form the product. So the reactant is here having so much energy, and this would be the threshold energy. Okay, the entire threshold energy that is required for the reaction to take place. But our reactant already has a certain amount of energy. From here, this is the barrier. This is the barrier that needs to be crossed in order to form the product. And so much will be the energy of the product. Okay, this product energy can either be low compared to the reactant or it can be high. Okay, that is a different concept where we study about endothermic reaction, where we study about exothermic reaction. We'll deal with that in the further classes. Okay, now basically I'm talking about the reactions where it is exothermic, as in the energy of the product is little less. Okay, This is our threshold energy, as I told you. Now, does it require so much energy for the reactant to go to the product? No. It requires only minimum energy, as in only so much is required. This is the minimum energy, which is our activation energy, which we need to provide for the reaction to take place in order to cross the threshold energy barrier. So once the energy, activation energy is being provided, here it forms an activated complex, okay? Intermediate complex is being formed. Once the intermediate complex is being formed, then it is easier for it to form the product, okay? This is how we plot the potential energy versus reaction coordinate graph, where we understand about activation energy. I hope this entire graph is clear, as well as the concept what exactly is activation energy and how it plays a crucial role for any of the reaction to take place. And this is how we can see the temperature is playing a role. So the temperature, how exactly it's playing a role? If we are providing higher temperature or if we are lowering the temperature, then only it passes through the threshold energy barrier, the energy that we are giving, right? That is in the form of temperature. That's what we can understand. So this was our activation energy concept. Now, the same thing we will see, as I told you right now, I told reactant giving product. It was for a forward reaction. Now we will see with an example where hydrogen and iodine react together to form hydrogen iodide. So how exactly is it going to be formed? What is the complex and how the reaction is happening with bond breaking as well as bond forming process? And along with that, we will see the graph as well, how we can plot it. Now hydrogen reacts with iodine to give hydrogen iodide. Now hydrogen is having this structure, and what exactly is iodine having? This is the structure of iodine. Both of these react together to form an intermediate complex. So how exactly is the intermediate complex formed, and where is the intermediate complex formed? This intermediate complex is going to be formed when the threshold energy barrier is being reached, as in it reaches that point. From there, it's going to break the bonds and then form the new bonds. Sorry, and it's going to form the product. Now, as I told, this is going to react and form an intermediate complex. This is our intermediate complex. This is our intermediate complex. So once the intermediate complex is being formed, there's bond breaking as well as bond forming happening. Hydrogen bonds break. Okay, this bond breaks and hydrogen iodide forms and hydrogen iodide forms, two molecules. That is when we can tell the product has been reached. That's why we have given here 2HI. This is how the reaction is going to be taking place. Now we will see that in the form of the graph. So when we are seeing in terms of graph, here you can see potential energy is there on the y-axis and x-axis has the reaction coordinate. This will be the reactant A. H2 and I2 are going to be reacting together. We are going to provide certain amount of energy in order to reach the, that is called the activation energy. Till it crosses the activation energy barrier, the threshold energy is being passed and activated complex is being formed here. That is what is this complex. And after that, once the activated complex is being formed, then we can see the product formation, which is going to be 2HI. Clear? Here, this part is delta H, as I told you. And this entire region is activation energy, but this entire region is threshold energy. Clear, students? So this is also a little important for your exam. They might ask you to explain what exactly is activation energy with an example or just the definition of activation energy. But basically, this concept, what is their activation energy, it is very important, as I told you in the starting of the session, for your further classes or for your further studies as well. This basic concept, if you understand, you can use it for a lot of things later, as in to understand a higher concept, to understand a concept which is a little more complicated. These activation energy concept and chemical kinetic concept plays an important role. Basically, it tells how exactly the reaction takes place in the molecular level. Okay, that's what has been happening here. So this is an example with respect to hydrogen iodide formation as well as the graph of it. Now, we know the Arrhenius equation, right? K is equal to A e to the power of minus EA by RT. We will plot a graph where we can see ln K and 1 by T. Here we are basically concentrating on how exactly the rate constant and temperature are dependent on each other and how does it play a role. And we are going to come up with a formula, one entire formula, which is going to be useful for your problem solving from your exercise or various kind of problems that comes for your exams. Okay, so we will start deriving that entire formula and we'll see how exactly rate constant and temperature is being dependent on each other. So as I told, first the Arrhenius equation is going to be K is equal to A e to the power of minus EA by RT, right? Now we are going to take ln on both the sides. So if you are taking ln, right? Now I'll just rearrange a little bit. Ln K is equal to, I'm going to bring this part here. One by T minus ln A. So this is basically nothing but y is equal to mx plus c. It is giving this equation where our m is going to be nothing but minus EA by R, which is our slope, as you can see here. So we have ln K and then there's one more 1 by T in the x-axis and ln K in the y-axis. So here this is the slope, fine. And this particular part is our intercept, that is ln A. As you can see here, this is our intercept C. And this entire thing is going to be a slope and the slope is negative minus EA by R. This is our slope. We derived it with our expression, that is Arrhenius equation. We derived it. Now if I'm taking log, okay, converting it into log, what am I going to get? From ln, I'm going to convert it to log right now. So 2.303. I'll just bring ln A this side. And when it comes here, sorry. This is what we are going to get once we are going to be once we are going to be converting it into log. Now I'm just going to take away 2.303. So I will divide it by 2.303. Okay, so once I divide it by 2.303, what am I going to get? Here it will be K is equal to A minus EA by 2.303 RT. Okay, this is going to be the entire equation where the log is being provided. Now this is the equation basically which is going to be used for all our problem solving, okay, which involves the rate constant as well as the temperature. Here again there will be different temperature which is being given, okay. Same temperature is not going to be given. So in such case, what are we going to do and how exactly are we going to understand the temperature as well as the rate constant is being dependent on each other. So basically, when we are taking two different temperatures for that matter, so first, if I'm taking T1 and the rate constant also will be K1. Now, if I'm taking T2, the rate constant is going to be K2. So here, this increasing temperature will result in increase in the rate of the reaction. The temperature as well as the rate both are being interlinked with each other. If the temperature is increasing, the same time rate constant also is increasing. That is what we are going to see here. Here as well as we saw, right? So as temperature increases, rate constant increases. Why is it so? Because of this particular equation. We can see here how temperature and rate constant are being interrelated to each other. There is a negative symbol here. That is the reason both of them will increase with each other. If it was a positive over here, then it's going to be inversely proportional to each other. Since it is negative here, both of them are directly proportional to each other. So when I'm increasing the temperature, at the same time I can see there's increase in the rate constant. Okay, so now we'll take two different equations and come up with a new equation again, which can be used for your problem, and we can see how they both are related to each other. So first equation will be where the temperature is T1 and the rate constant is going to be K1. So in that case, we can see if you are taking the ln, right? Basically ln K1 is equal to ln A minus EA by 2 point, sorry, it's ln R and T1. This will be equation 1. Whereas the second equation is going to be ln K2, which is going to be equal to ln A minus EA by R T2. I'm just going to subtract 2 by 1 as in equation 2 by equation 1. So equation 2 minus equation 1 is going to give us ln K2 minus K1, which is going to be equal to ln A minus ln A is just going to go here, minus EA by R sorry, T2, and again minus of minus EA by R T1. Okay, so here minus EA by R T2 and here minus and minus is going to become plus, basically EA by R T2 plus EA by R T1. Here it's going to be ln K2 minus K1, which can be written as fine. It can be written as this way. It can be written like this, K2 by K1, as in the subtraction is going to be written in this particular way. Now again, how exactly can I write this? This can be written as EA by RT is common, right? EA by R is common. T is the only thing that is being changing. So here it's going to be 1 by T1 minus 1 by T2. 1 by T1 minus 1 by T2. EA by R. We are just going to cross multiply here. T2 minus T1 by T1 T2. And this would give us a new equation where we can see when two different temperatures are given and when there is two different rate constants, we can use this particular formula and solve the problem. Okay, and this even tells how K and temperature is being dependent on each other. We started off from that and we came to this particular equation. The same equation can be written in the form of log as well. So if they're given something in the form of log, you can write it in the form of log and solve the problem. Clear, students? So this would be the end of what exactly we studied today, temperature dependence on the rate of the reaction, as well as the activation energy. So I hope you have understood how the temperature dependence on rate of the reaction is going to play a role, which is a major factor which affects the rate of the reaction, that is temperature, as well as the temperature dependence is being related to the concept activation energy. So I hope you have understood that as well. So in the next class, as we know, we are going to be studying about what exactly is collision theory. So we know the reactants, okay, when we are writing the Arrhenius equation, we saw there's certain amount of energy which is already there in the reaction, okay. So sometimes, so what happens, this the energy what already the reactant is having, they will that energy, the collision energy, whatever we say, that kinetic energy is much more, okay. Kinetic energy is much more compared to activation energy. That is when we can tell the molecule is unstable and they start reacting with each other. So how exactly they're going to react with each other, which are the molecules which has high kinetic energy, and what exactly is the procedure over there for the reaction to take place, or how the reaction mechanism is going to be, all of these things we'll be studying in the next class. So we'll meet in the next class. Until then, stay tuned to Vista's Learning. So you can access to all the subject videos from our Vista's Learning in our YouTube channel as well as in our web application. So if you have missed any of the videos in our YouTube channel, you can always access it in our web application. Our web application would be www.v-learning. So as I told, I'll meet you in the next class. Until then, stay tuned to Vista's Learning.